Okay, section 11.3, video 2. So the second part of this section is about estimating the sum of a series, not just knowing whether it converges or diverges. So we just learned the integral test, which tells us, or can tell us, whether a series is convergent or divergent. So if that series is convergent, what if we want to know what the sum is, or at least a best guess, a best estimate? Well, any partial sum that you can figure out would be a decent approximation because we know that the sum of a series is simply the limit of the partial sums. We talked about that in 11.2. So the question then would be, how good is the approximation of Sn? What if you don't have the ability to find the partial sum where n is very large? Or what if you're just curious how far off you are? So to figure that out, we need to look at something called the remainder, capital R sub n. Capital R sub n is just basically your error. So R is S minus Sn. So S is the actual sum of the series and Sn is the partial sum. So that remainder, S minus Sn, is shown to be an plus 1 plus an plus 2 plus an plus 3 and so on. So the remainder R is the error made when Sn, the partial sum, the sum of the first n terms, is used as an approximation to the total sum. We use the same notation as the integral test, assuming that f is decreasing from n to infinity. So if we compare the areas of the rectangles with the area under the curve itself, what can we figure out? Well, if you look at the first one, Rn equals an plus 1 plus an plus 2 and so on. And if you look at the picture, you can see that if you added up all these areas, A for area, an plus 1, an plus 2, an plus 3, and so on up to infinity, all those areas added up are definitely going to be less than, at least less than, the area under the curve itself. So that's what this first one says. This remainder will be less than or equal to that integral from n to infinity. And then if you look at the opposite, if you have the same setup, but you're using the left endpoint, so all of your rectangles are larger, then you know your remainder is going to be greater than or equal to that integral from n plus 1 to infinity. And the top one is the integral from n to infinity. So then we have something called the remainder estimate that goes along with the integral test. Okay, so suppose f of k minus a sub k, where f is the function, and remember it has to be continuous, positive, and decreasing. In this case, when x is bigger than n, and then sum of a sub n is convergent. If all of that's true, you have a positive, continuous, decreasing function, and the sum of all those areas is convergent, then you know that if R is S minus Sn, which that is the definition of the remainder, then we have that the integral from n plus 1 to infinity is less than or equal to your remainder, which is less than or equal to the integral from n to infinity. So what you see here is a lower and upper bound containing the remainder itself, which is our error. So let's look at an example. I think it'll make a little bit more sense. So part A says approximate the sum of the series 1 over n cubed, which is a p series, by using the sum of the first 10 terms, and then estimate the error involved in this approximation. So they're asking for R here. And then part B says how many terms are required to ensure that the sum is accurate to within 0.0005. So here they're saying, how many of these terms do you have to add up, or how high does the partial sum have to go until your remainder, your error, is this small? So for the solution, for both of these parts, we're going to need to know the integral from n to infinity of f of x, which is 1 over n cubed turned into a function would be 1 over x cubed. Okay, so 1 over x cubed definitely satisfies the continuous, positive, decreasing conditions. So we can set up the integral. So we have the integral from n to infinity of 1 over x cubed would be the limit as t goes to infinity of the integral from n to t of 1 over x cubed. When you integrate 1 over x cubed, you get -1/2 x to the negative 2. So negative 1 over 2x squared. That's the antiderivative of 1 over x cubed. So then we apply the t and the n, the limits of our integration, and we have negative 1 over 2t squared plus 1 over 2n squared. So when we take the limit as t approaches infinity, that only applies to the first term, because notice the second term doesn't have a t in it. N is some other value not involved in this limit. When we apply the limit t approaching infinity to this first term, 1 over a huge number, remember that's going to go to 0. So this whole first term has a limit of 0, and all that's left is the second term. So the limit of all of this is 1 over 2n squared, which means the integral from n to infinity of 1 over x cubed is 1 over 2n squared. Okay, so now to actually do the problem. If we approximate the sum of the series with the first 10 terms, that's what we have written here, 1 over 1 cubed, 1 over 2 cubed, 3 cubed, and so on up to 10 cubed. If you add all those up in your calculator, you get about 1.1975. Okay, so to go back to our remainder estimate, we know that R10 should be less than or equal to the integral from 10 to infinity of 1 over x cubed. Well, we just found on the previous slide that an integral from n to infinity is 1 over 2n squared. So 1 over 2n squared we'll replace with 10. So 1 over 10 times 2 squared ends up being 1 over 200, which means if you use the 10th partial sum to estimate this series, your remainder at most will be smaller than 0.005. Now in part B, they want one more 0, 0.0005, and want to know how big n has to be to get there. So we know that our remainder, our r, is less than that integral from the integral test and the remainder test, which we already calculated to be 1 over 2n squared. And we want that 1 over 2n squared to be less than 0.0005. So this isn't a new calculus problem, this is just solving the inequality for n. So when you solve that inequality, you get that n must be greater than the square root of 100, which is 31.6. So to get to a whole number, because remember series aren't defined in between the whole numbers, then we would have to round up to 32. So the smallest partial sum that would satisfy this condition in part B would be the 32nd partial sum, meaning the sum of the first 32 terms. And that'll get us the accuracy within 0.0005. All right, now if we're working with, if we go back, to the integral test and the remainder test and add partial sum to each side of the inequalities in 2, what do we get? We have the partial sum plus the integral is less than the true sum, which is less than or equal to the partial sum plus the integral from n to infinity. So what this does is, like we mentioned earlier, give us a true upper bound and lower bound for the actual sum s. S is the sum of the series. So if you have the two integrals and you have a partial sum, you'll have an upper and lower bound for the true sum. And that ends section 11.3. Thanks for watching.